Have you ever stopped to think about why a for loop works pretty much the same way no matter what programming language you're using? It's not a coincidence. It's because under all that syntax, there's this deep, fundamental architecture. And today, we're going to dive into that hidden world, the really elegant math that makes all of our software possible.
So what is this secret language that every piece of software seems to speak? Nope, it's not Python, it's not Java, it's not C++. It's something way, way more fundamental. It's a universal language of pure logic and structure.
We're here to really dig into what one of our sources calls the elegant mathematics and profound categorical structures that enables software functionality. That sounds pretty intense, right? But in simple terms, this isn't just about how to code better. This is about the absolute bedrock of what computation even is. Okay, so to understand this language, we've got to start with the deep structures of computation. We're going to begin with the most basic, but honestly the most powerful building block you'll find in just about any complex program. And that building block is the recursive data type. Now, the idea itself is actually kind of simple, but it's incredibly profound. It's just a structure that's defined in terms of itself. Think about a file system on your computer. A folder can contain other folders, right? Or a family tree, where a person has parents, who are also people. This self-referencing pattern, it's literally everywhere in software. All right, stick with me here, because this gets a little abstract, but it's super important. In the world of formal computer science, these recursive data types aren't just some clever programming trick. No, they're actually defined as the solutions to mathematical equations. But these equations only work inside a special mathematical universe called an algebraically complete category. You can think of it as a kind of sandbox where these recursive definitions are guaranteed to make sense and not, collapse into a paradox. And it's that level of mathematical rigor that lets us build tools that can reason about our software with total precision. So if we have these amazingly powerful recursive structures, how do we actually talk about them? How do we describe them? Well, we need a formal language, a system to lay out how they behave and what we can do with them. And that language is called iteration theory. So what in the world is iteration theory? Well, at its heart, it's really an algebraic framework. It's a system that was built specifically to study the three core things that almost every program does: doing things in a sequence, making a choice, like your classic if-else statement, and of course, iteration, repeating something in a loop. It basically gives us a pure mathematical way to talk about program flow. But, science never stands still. The original theory was fantastic for modeling the flow inside a single program. But what if you want to model how entire programs or systems relate to each other? For that, we needed an upgrade. Enter iteration 2 theories. This is a much more powerful generalization that doesn't just look at the steps inside a process, it models the transformations between different processes. So that's the next logical question, right? What are these more powerful theories actually made of? What are the components? It really builds up in 3 layers. First, you start with something called a 2 category, which is just a fancy way of saying a system that can describe not only processes, but also the relationships between those processes. Second, you add what's called a Cartesian structure. This gives the system a way to combine things, like running 2 processes at the same time. But the real secret sauce, the magic, comes in step 3. You introduce the dagger operation. And this dagger operation, this is the real game changer. It is the mathematical tool that lets you formally create a feedback loop. But it's so powerful that it captures the idea of recursion, not just for what happens inside a program, but for the relationships between whole programs. It's the mathematical engine that lets us describe these incredibly complex, interconnected systems. Okay, I know what you're thinking. That is a lot of abstract theory. But how does any of this connect to the real world? Where does this math actually pop up in the code that you and I write every single day? While the applications are way more direct than you might think, this theory is the backbone for designing things like algorithm flowcharts. It helps us formally define what a programming language's rules even mean. It's even used to build tools that can generate correct code all by themselves. It's the framework that compilers use to understand and manipulate the very structure of your code. And this right here is where it all clicks. This is where the super abstract theory becomes totally concrete. All those fancy mathematical terms, they map directly to the code we write. Composition in the theory, that's just you writing one line of code after another. Choice, that's your if-else block. And iteration, well, that's your for loop or your while loop. You see, the math isn't some separate thing. It is the formal description of your code.
And its power goes way beyond just simple programs. This framework is so robust that it can describe the incredibly complex dance of communicating processes. Think about servers all talking to each other across a network. It models these interactions using a special structure called a synchronization tree, which is basically a perfect roadmap of every single possible way those communications could play out. It just goes to show how versatile this mathematical language really is. All right, let's zoom out one last time and just see where these iteration 2 theories really fit into the grand scheme of things, into the whole wide world of theoretical computer science. It turns out these ideas belong to this massive, profound field called abstract and axiomatic computability and recursion theory. I know, it's a mouthful, but this is the part of computer science that asks the biggest questions of all. What actually is computation? What are its absolute limits? And can we build a perfect logical language to describe the whole thing? And what's so fascinating is that this field is like a giant meeting point. You had all these brilliant researchers working on what looked like totally different problems, using different tools, least fixed points, recursion categories, type theory. And they all found that their work was leading them back to the exact same core principles about computation. It's like they all started digging in different places and hit the same treasure chest. They were all uncovering the same fundamental truth. Which leaves us with one last really big idea to think about. We've seen that the code we write isn't just a list of instructions for a computer. It's a form of applied logic that has this incredibly deep mathematical structure. So, if we keep perfecting this mathematical language, what new kinds of possibilities can we unlock? What kind of smarter, more reliable, maybe even more powerful software could we build in the future?